So one thing I don't want you to lose sight of is that it can take some creativity and trial and error to find the transformation that's going to work. And that was true with U substitution, but you're at this point now where you've done U substitution so much and for so long that you're kind of used to it. It's going to take a lot to get used to doing this type of transformation with two different variables changing, not just one. So have patience with yourself. Try to work it out. Okay, so there's two ways or reasons to do transformations like this. One is to make your integrand simpler, and the other is to make your region of integration simpler. Like those are the two big reasons that we would do this. Now, this example is going to be of number one because our region's not particularly difficult. I mean, it's some points, it makes a parallelogram, it's fine. But this integrand is not so fun. So this is going to be a case number one. We're going to make our integrand simpler. All right, now how are we going to do that? Well, trial and error. We try different things. So I'm going to let u equal the 2x part, 2x. And then I'm going to make it be the rest of this because I want to transform this function from an x and a y to a u and a v. So I'm going to let v equal y minus 2x, which you'll notice 2x is actually u. So in other words, v is y take away u. That leads to that. Okay, now give yourself some space here for a second. So this is not how we define the transformation. So the transformation has to be defined as x equals some function of u and v and y equals some function of u and v. And we kind of have the opposite, if you will. We've defined u and v. So we have to transform this into a transformation. Okay, so x would be u divided by 2. So this is our transformation t. We're going to let x be 1/2 u. And we're going to let y be, if we solve this for y, it'd be u plus v. That's our transformation. And it's often the case, actually, that when you look at it, you try to define your u and v first, and then switch over to the transformation in terms of x and y. That sometimes happens. It's not a big deal. So we just do that. Okay, so this is our transformation. This is our officially transformation. So we need our Jacobian. The Jacobian is the determinant. I keep trying to say discriminant. Determinant. xu, xv, yu, yv. Okay, so that would be equal to, actually, I've got to put this in a different space. 1 second. There, down here I'm going to have some room to groove here. Okay, so xu. So I take the derivative of my x function with respect to u, which would be 1/2. Then I take my derivative of my x function with respect to v, which is 0 because there is no v there. My derivative of my y function with respect to u would be 1, and the derivative of my y function with respect to v would be 1. So the Jacobian would be 1/2 times 1 minus 1 times 0, which is 1/2. All right, so the Jacobian is all figured out. You figure out the Jacobian from the transformation. Now we have to think about our region of integration. Our original region of integration was R. R was a parallelogram with vertices 0, 0, 1, 0, over 2, up 4, and over 2, up 5. So it looks like that. This is the region. Now we need to transform this region to a new zone. Now I think it helps to kind of think about the old points that you had, which were x's and y's. That was 0, 0, it was 0, 1, it was 2, 4, and it was 2, 5. And now we're going to write them in our new system. So our new system is going to have them be u and v. Now u we've already defined. See, this is why it's so helpful. It's helpful to have both of these things, right? This is the official transformation to find the Jacobian. This is super helpful for finding these values. So u was 2x, and the v was y minus 2x. So let's think about how that changes those points. So 0, 0. If I put 0 in here, 2 times 0 is 0. Y, which is 0, take away 2 times 0 is 0. So that point becomes the same point we already had. No problem. All right, what about 0, 1, which I wrote wonky for no reason. All right, 0, 1. There we go. Okay, 2 times 0 is 0. Y minus 2 times 0. So that's 1, take away 2 times 0. So that's 1. So far, nothing's changing. Yay. Okay, now what about 2, 4? 2 times 2 would be 4. 4 take away 2 times 2. So 4 take away 0 would be 0. And then again, 2 times 2 is 4. 5 take away 2 times 2 would be 5 take away 4, which is 1. So our new zone over here, this is S, the new region of integration. Instead of being this parallelogram, let's think. From 0, 0 up to, used to go from 0, 0 to 2, 4. That side right there would go from 0, 0 still, but what was 2, 4 becomes 4, 0. It goes like that. Okay, then we used to have a side over here between 2, 4 and 2, 5. Right, 2, 4 and 2, 5 now goes from 4, 0 to 4, 1. So it looks like that. All right, then we used to have a side up here at the top that went from 2, 5 to 0, 1. And so now it's going to go from 4, 1 to 0, 1, and it's going to go straight that way. But straight. It drew mine a little wobbly. And then you can guess where this is probably going. That last side right here, from 0, 1 to 0, 0 is right here. We have a new region of integration, right? It transformed from a parallelogram to a rectangle, which is much easier to work with as well. So we actually got a 2 for 1 here. We did this to make integrand simpler, but the region of integration also became simpler. So it worked out really nicely for us. Of course, we have to do that integration, and I'm going to in a second, but I just wanted you to see what's happening here. So we have this parallelogram, that's the original, and it transformed into that rectangle. Right, so that's what's happening. Now we haven't done the calculus bit yet, so we still have to do that. So we have to take our original integration up here, and we're going to transform it. So the original integral, here, let me do it with a different color. That original integral r of the square root of 2x times y minus 2x dA becomes the square root, that was u, this is v, so the square root of u times v, and then we have to put our Jacobian in, so absolute value of the Jacobian actually, so it's a half, right? I should have mentioned that. So absolute value of a half, and then we have to decide if we're going to go dv du or du dv. It doesn't really make a ton of difference. I'll just mention, I should have put this up here before. This is the u-axis now, and this is the v-axis. So if we go this way, vertical, as we're usually used to doing, that's dv du. right? So then down here we would go dv du, and this is a rectangle, so you don't get much easier than that. U goes from 0 to 4, v goes from 0, I should have put that value in, that's 1. It's right here, 1. Okay, so we're going to go from 0 to 4 for the u, 0 to 1 for the v. And I'm going to make a couple notes of things. I'm just going to make a note that the region of integration is easier. Yay. Woot. But I'm also going to notice this guy right here is really u to the 1/2 times v to the 1/2, right? So I can integrate that pretty easily with respect to v, because I'm going to go v first. And the half, this is the absolute value of a half, which is a half. So I'm just going to pull that out in front. So it's 1/2 integral from 0 to 4. And then I'm going to integrate v to the 1/2. And I'm going to leave the u to the 1/2 sitting there. So the u to the 1/2 just sits there. The integral of v to the 1/2 would be v to the 3/2 times 2/3. So I can choose to put the 2/3 here, or I can just say, hey, wait a second, that's a constant. So let me just throw a 2/3 out in front and multiply it by that. So that's what I'm going to do. And the v is going to go from 0 to 1. All right, so sorry, something stuck in paper. There we go. There, I got it. Okay, so then we're just going to put 1 in here and 0 in here. Well, that's just 1, right? 1 to the 3/2 is 1. Take away 0 is 0, so this is just 1. And then du, we haven't done our du yet. Okay, so this becomes 1/3 integral from 0 to 4 of u to the 1/2 du. And again, this is just really easy. So that's 2/3 times u to the 3/2, u to the 3/2 from 0 to 4. 2/3 times 1/3 is 2/9, and then this will be 4. Square root of 4 is 2. 2 to the 3rd is 8. So this is 2/9 times 8, which is 16/9. All right, so that's a lot of work, but think about what you're doing. It's way more complicated than just a one variable transformation. This is u sub on steroids, right? So you find your u and your v, and it can take a while to figure these out, right? Your u and your v are right here. Then you use those to figure out your official transformation in terms of x and y. You use the official transformation to find your Jacobian. Technically, you need the absolute value of the Jacobian, but that's all right. Then you have to change your region of integration from what it was originally in x and y to what it now is in u and v. Right? That can take some doing. Then you rewrite your integral, not with one transformation, but with 2. You put the absolute value of the Jacobian in there, and then dv du with all your new limits of integration. And then you integrate.